Welcome to CNC Machinist Made Easy, where you can learn to machine right at home, especially, well, not all of it, but 90% of it. Tonight we're on video 6, blueprint reading. I want to go with you, along with you, in this little adventure here and show you a little bit about how to look at blueprints, some things that you'll naturally and normally see on blueprints to give you a better understanding, whereas when you would visually see one in real life, you would know what to expect. Blueprint reading. So let's go here ahead. Let's take a look at a simple blueprint right here, or should we say a part. You're familiar with similar images like this as we did our X and Y and we did metrics, but let's take a look at this part right here. We can see right there, this is the same part. Right up on top here, let me see if I can get this pointer right there. See that pointer right there? Right up on top here, it's showing us the same piece that this is, except it's just showing it from the view of the edge of the part. Is if I would take something like this thing right here and I would just show it to you from this way, and I would also show it to you from the edge. Okay, so you're looking at this, it's notifying us right here that we're dealing with 0.125 thick stock. Okay, now 0.125 I know personally is an 1/8 inch. You'll learn these because it's when you work them long enough, it doesn't take very long at all, and you can better understand just looking at it spontaneously. But if you go back to the videos of decimals and fractions and how they convert and do a little old research, it'll be a lot easier when you run into it in real life. Now we've got a piece of 1/8 inch thick stock here, and if we take that and flip it upright, we see it's 1/8 inch by 1 inch over here, and we see that it's 4 inches long, and they want a hole in it. And the location of that hole, if my zero were over here on the left, the location of that hole is going to be 1 inch in the X, and it's going to be a half inch. Right here is 500 thousandths, the 3-place decimal, which is a half inch from the bottom, a half inch up. 1 inch X, a half inch Y is the location of that hole. Now notice right here, I just want to go over a few things here as far as basic things you'll see on a print. Notice right here they have 0.531. That says 0.531 plus or minus 2 thousandths. Again, as you can see, there's a 3-place decimal there, and we say thousandths with a 3-place decimal, and it's 2 thousandths. 2 thousandths is probably the thickness of the human hair. So they're saying, I want you to put that hole in there, and I want the diameter, and it says right there through. So they want a hole that goes completely through the 1/8 inch, which you're verifying that right here from the side angle, that hidden line goes right through that piece. They want a hole 0.531 at the location of X1, Y 0.5, and I want that diameter of that hole to be plus or minus 0.531, or could we say 531 thousandths? Okay. Now again, when you learn those fractions, 1/8, 1/16, 30-seconds, you learn them, and you're going to have a good understanding as to what that fraction is. That's a 30-second above a half inch, which is 17 30-seconds. But like I told you, the reason they went with decimals is because they want to pinpoint right where they want to be. So they said 0.531 or 531 thousandths plus 2 or minus 2. That'll allow me to go to 529 thousandths and all the way up to 533 thousandths. So that'll give you a better idea. That's just a basic print right there. That's all you're doing, putting a hole at that location, at that diameter, and that part. And I had that slide already. That's what I want you to notice. That's what we went through. Let's take a look at this print one. I want to show you something right here. You see this print has 4 holes in it, and in the side right here, it's got showing it looking down at the piece as if it were in your vise. And over here, if I would take that, you're looking at it in your vise, looking down at it in your vise, and now they're telling you also, they're giving you a view from the side angle, which is right here. Okay. Notice this symbol right here. What that symbol means is that's going to be your absolute zero, or that's where the engineer who designed this print has established his zero. Right there, he wants all these holes to reference off that established zero. You can call that a datum. That's a fancy word for zero, XY zero, or your absolute, where your absolute zero is. And I'll tell you why that's absolute, because if you see this dimension right here, this half-inch dimension in the X, it's off of this zero, so that's absolutely a half inch. However, this 1 inch dimension up on top moves 1 inch incrementally. It's not off the absolute 0. It's off the last location. So I would call that dimension an incremental dimension. I would call this dimension an absolute dimension. That might not seem significant to you, but when you start getting into G codes or other more heavy-duty programming, you'll see why that can be very beneficial. Note that. Remember that I told you that this is an absolute dimension. That means it's coming off your absolute 0. Whereas this dimension is only telling you this is 1 inch from that hole to that hole. It's an increment in increments. As you look here, they want you to drill 4 holes. Your 0's there. Challenge yourself and tell me what the location of this hole is. The location of this hole would be x, 0.5, y, minus 0.5. What would this one be? It wouldn't be x1. It would be x1 plus the 0.5. Some prints show incremental dimensions. Some prints will show absolute dimensions. Some prints will have their 0 or their datum over here. Some will have them over here in the center. Some will have them down here. And you'll get into that. The most important part is understanding what's being asked of you. And you can see right here, they're asking that hole to go 3/8 deep. They're telling you don't go through. They're telling you that part is a 1/2 inch thick. Okay? Notice, like I said, that datum right there. Some of these prints are a little bit blurry. You see, here's another one. Now notice where that datum is. It's in the middle of your part, right there. In the middle is your 0. And they're telling you, come up 0.625 to the x and 0.625 to the right, drill a hole. And come down 0.625, which is x negative 6.5 and y negative 6.25, excuse me, to drill the other hole. Okay? And you're going to have the hole go all the way through, we can see. Sometimes they'll say through, sometimes they won't. Let's look at another example and make sure we get this. Here's a part right here. I'm not going to go crazy with it. They're telling that they want M8 times 1.25. It's just a tap, like you have a 1/4-20 tap. When you get into the metrics, they have an M8 tap. That means the M8, it's an 8-inch diameter as a 1/4 inch. And it's a 1/4-20 would be the pitch. A 1.25 would be the pitch. It's slightly, we'll get into that when you start transferring metric taps and standard taps. Not really a big formula, something easily to understand. But today's lesson is understanding. Right here we have 10 millimeters, okay? And then we have 30 millimeters. And now notice, all these dimensions are absolute dimensions. They're coming right off that absolute side right there. Our datum is down here. And all of these dimensions are absolute dimensions. It makes it nice often for machining. Certain times incremental dimensioning comes right, but that's for another day. And they're telling you the part is going to be 20 millimeters thick. They're telling you the datum is right here, right there. And they've got your locations for each and every hole for you to plug into your machining center. I want to go through something right here. Notice your datum right here is at the bottom of the piece. Imagine I take a vise, and I crunch that piece in there, right? I've got my back jaw will be here, my front jaw will be right there, and I got that piece in my vise. I want to share with you something you might want to keep in your mind. This 0 is on the back jaw. Now, let's take a look. Now, if I take that and rotate that part, now that's 0, I'm going to go back. See that datum that's up there? If I take that part and I rotate that, boom, it's actually up there. And if I rotate it again, boom, I'm upside down and now it's right there. What would make me possibly want to do that and just take the dimensions that way? I'll tell you what. There's a vise. There's a standard machining device. Notice the back jaw is stationary. It doesn't move. It's the front jaw that moves. So if I take that, the back jaw is stationary. So if I take that and make that the back jaw, if I have multiple pieces, let's say, and let's say this piece down here is each one's just a few thousandths different. If I have it on the back jaw, the 0, or the jaw towards me, the front jaw, whatever you want to call it, let me go back. If I have it, my 0 on this jaw, that 0 could always be different if the material is slightly different, and that would make your holes just a slight bit off. Now you got to ask yourself, how accurate, how consistent are your pieces? And you have to ask yourself, what type of customer I have here? Where's my 0 right now? What do I want to do? it's very good to learn to start putting your zeros, if you can, on the back stationary jaws. You can have 1,000,000 pieces, and that number right there, 10 millimeters, is always going to be 10 millimeters. And no matter how you look at it, no matter what you do, because that back jaws, there might be a little variation down here in the front jaw, but when the customer comes up and says, hey, this isn't right, there is no call-out dimension there. The dimension that he's asking about is right spot on. Then here's another print. Let's take a look at that one. Some of them can get a little crazy. For the most part, depending on the customer. But you take a look at this print, all sorts of dimensions. Where's your zero? Well, I wish I could just get out of there. No, that didn't work. Present. And right there. Let's take a look at the zero. Right. Oh, let me just give me a second. Oh, so we have just give me 1 second here. Let me try to get this so I can get that out of there. We have a dimension here. Now look at this. They're telling you that chamfer is going to be 10.61. There's a lot more easy ways to do it than that. This is a rare print. However, I want to introduce it to you. You'll run across it at times, depending on the designer. Now you look at this one right here. The dimensions are 10.5 up, 36, 86. They're coming off of this absolute zero, but then right here they decided they wanted to go 47 from there to there. In the Y dimension, they say they wanted to go 80 across, and then they're telling you that they want 47 inches or 47 millimeters. It could be inches, but you'll know the difference if the customer wants a 47-inch piece or a 47 millimeter piece. It's the 25.4 times bigger or smaller. And right here, they're telling you they want 38.2. It's just very difficult, some of these prints to follow. So now you got to get your kick out. They have a center line right here. The center line means these holes are all centered. So 47 millimeters, you could take that divided by 2, and you can put your zero in the middle, and you can say 47 divided by 2 would be that location in the negative and this location in the positive. Some people just sit down and get a pencil and paper, find an absolute dimension, and they write them all out. Some people will download a DXF file or a DWG file, which already is the file, the very digital file. And if you have software, which we'll get into, you don't care where your zero is. You care. You decide where you want to put your zero, and everything will work it out for you. But that's, again, not today's topic. Now, I want to share with you just quickly about lathes. We have X, Y, and Z. Now, you'll notice your Z in your vertical machining center always is with the spindle moves. Your horizontal machining center is a horizontal spindle, and your Z is always into the depth of the part where the spindle moves. In your lathe, in your common standard lathe, you have 2 dimensions, your Z and your X. Your Y is when they get more into advanced stuff, which you don't need to know right now. But your X and your Z, again, lathe is the same thing. Your tailstock or your drill that goes into the part, let me see if I haven't noticed, that's your X, is going to be, into your part is going to be your Z, which is right there. That's where your spindle is going into the part or your profile. And your X is going to be how far away that carriage goes to make that 2-dimensional profile. So note that when you have a lathe, you're not dealing with X, Y, Z. You're dealing normally with Z and X. Z is drilling into the cylindrical part of the face of it, and X is profiling any contours as it spins. Something, if you're interested in lathes, make sure you keep going through that. There's a lathe part. As you can see, it's 2Ds. It gives you your Z. It gives you move out to your X, and it's what it is right here is a contour. It's a 2D contour. Your part's spinning, so all you need to do is a 2D contour right here, and you'll rough it in and work your way down there, and then you'll make finished passes, and you'll have a piece like that. That's how lathes operate. Now what I want to do, let's add this information into your standard blueprint. There's that part we just looked at a lathe. We don't know what that part's made out of. There's so much detail that we don't know about this. We know the dimensions, what we went through, and up to this point, that's all you ever saw was a view. But let me show you what a blueprint looks like. Now that's added to a blueprint. What you call the outside of that is your border, wouldn't you know it? And down here, let me see if I can get that pointer back. Down here, you have what you call your title block. Oftentimes up here, you'll have a little bit of added information, whether it be material or some notes they want you to know. But down here, you have what you call your title block, okay? Down here. And there's a lot of things. Let's go through some of this title block information and some necessary things that you're going to think, maybe I don't know, but you will need to know. Let's take a closer look at another title block. Right here, we have a logo often, and we have the name of the company, if it would be. Right here, we have the title of that part. If they want to call it a block, like we were looking at a few blocks, they'll say this is a block. Normally, each one is assigned a print number. That number corresponds to that print when you pull it up in your records or their records. Now you can see cage numbers here. 9 out of 10 times, a lot of this stuff is for the customer's sake. They want to look it back up, who typed it, the date it was typed. But what I want to focus on having explained that is a few things that you'll need to know as the machinist. And one of them is that part right there. That part right there tells us you have, if you zoom in on it, I wish I could zoom in, but it has point XX corresponding or resembling a two-place decimal. So if I'm looking at a print that says .20, let's say they want a .20 hole put in somewhere. They don't say .200. Let's say they specifically say two-place decimal, .20. If they do that, they're telling you that the tolerance on that part is plus or minus 30 thousandths, okay? Oftentimes, the customer will tell you, or that print will notify you how tight that tolerance is by how many zeros they carry out in the dimension. Right here they say, if it's a three-place decimal like .2 or .020, which would be 20 thousandths, they're telling you, because I put that dimension 3 places over, I am telling you I want you to hold 10 thousandths tolerance of that either location, of that diameter, of that thickness, whatever it is. If it's 3-place decimal, the tolerance is 10 thousandths. That's one major, in fact, the most major important way a print will notify you how tight that tolerance is. Right here, it's got an angle sign. Any angle it's saying is with some plus or minus 1 degree. You have 1 degree of lenience, grace, or tolerance, whatever you want to call it. Okay? Here's another print, same thing. It's showing them tolerance. It's a little bit more easy to see possibly. Right here they're saying the angle is plus or minus 1 degree. And the print is saying if I have a 1-place decimal, it's 60 thousandths. That's about a 1/16 of an inch. That's really nice tolerance. They're telling you just take a drill and plow that in there. They're telling you shoot that over there and get that in there. Now today's technology, it'll put it a lot closer than that. But they're telling you, you do have that tolerance. Oftentimes that will... if you have your own machine shop in the future, have a lot to do with when you're bidding what that customer's asking for, which will in turn give you a better idea and allow you to be more competitive as far as how you want to go about making that part. If they want 1,000 tolerance and dimensions and hole diameters and all that, it's going to take you more time. Your machines can normally do that, but it's going to take you more time and you have to bid accordingly. But then you have your 3-place decimal. Notice your 4-place decimal. They're .0012. They're getting a little tight there. Their machines nowadays will shock you how they can fly 40 and 50 inches and go right back to that part within the half of a human hair. Don't even think about it. You got a good machine, it's not even anything to think about. You can tweak them numbers right in there. It's actually quite impressive. Another part of a blueprint title block I want to notice is this part right here. What you call that part is a third angle projection. You're thinking, well, what is that? Let's take a closer look what that is. This is a third angle projection. You see that cone right there is showing you 2 dimensions of that cone. And if I take that cone, I'm going to try to do this here on TV, and if I flip that up this way, you're going to see the top of that right here, and you're going to see the bottom of it down there, aren't you? But what's to say if I took that piece and turned it this way? You wouldn't see that round piece, would you? Because you'd be looking at the bottom down here from this way. So they're telling you this piece of a third angle projection is informing you that this piece needs to be turned this way. Well, what is that? What are you talking about needs to be turned that way? Let's see if I got something here. Let's take a look at that image down there. You see this hole goes through there? They're telling you, I'm going to use this little thing. I should have had this earlier. They're telling you to take that piece down here, and they're saying you have to come out this way. You see? So they're saying take this piece and come out this way. Okay? This way. They're telling you from the side, That's the way you got to flip that piece this way. See, just like the third angle projection. And that can be important. You're thinking, well, them are through holes. I can put that in there. It's all square. It's just this print. Let's take a look at this one. What about when they don't have through holes? They're telling you take that part and go through this way. If the line is hidden, dotted, that means it's a hidden line. That means it's something that's on the other side or in the part. Okay? That means it's not at the surface. A dotted line is known as a hidden line, and that means it's looking through the piece as if it were transparent. A solid line is only you can see at the surface, is only what you can see. So now you take a look at what you have here, and you think, well, I can take that and turn it every way. You're right again. But there are, you call that concentric. We call it concentric. When the part is concentric, that means no matter which way it works every time, because everything's even from this side to that side. Oftentimes they're not concentric, they're irregular, and then you will have to know that third angle projection to know what angle it's coming from. So tonight we went over dimensionings. I know I got a little long-winded. I want to keep these videos short, and take a look at it. If you have to watch it once or twice and get a good understanding of how these prints work, don't get overwhelmed. Most of these prints a lot of times are a lot easier, and when you take and look at a print a few times and just look at it and think about what you're looking at, it all comes together, and as you progress in it, you'll be surprised the complexity of some of these prints that you can interpret and look at and know what it is that they're asking of you. So thanks for watching CNC Machinist Made Easy, and we'll see you on the next video.